In this video, we're going to look at the periodic properties involving ionization energy. Ionization energy is crucially dependent on our understanding of effective nuclear charge and how we use the effective nuclear charge to understand aspects of the size of atoms and ions. So we will be predicting and explaining aspects of ionization energy, but it's really closely linked to these previous ideas. Here I share a lot of information pertaining to effective nuclear charge. We need to be able to calculate the effective nuclear charge and understand it conceptually. The effective nuclear charge is balancing the attraction that we have between the nuclear charge, the number of protons, and a particular electron, after accounting for aspects of shielding or repulsion from one electron with another. We're interested in the net attraction a particular electron experiences. It's easy to figure out the nuclear charge. We can just look for Z, the number of protons. And in a simple approach for counting the shielding and accounting for that, we consider the previous noble gas, that number of electrons, to be ones that are core electrons that are shielding. That allows us to then better understand the size of atoms and ions. We see data shown here. As we move down the periodic table, down a column, we see the size of neutral atoms dramatically increasing. We are filling the principal quantum numbers are increasing. N equals 1, n equals 2, n equals 3. The principal quantum number describes the size of that orbital. So if we're moving down, we're populating larger atomic orbitals. But I see a clear pattern as I'm moving left to right. That's best explained in terms of the effective nuclear charge is increasing, and I see a contraction as I move across the periodic table, and then I move to a larger n value. Notice how the effective nuclear charge was an important part of this analysis. Moving to then trends involving size, the idea is that anions are larger than cations. Why is that? Cations are smaller than their neutral atoms because we're removing electrons that had been contributing to electron-electron repulsions. For anions are larger than their neutral atoms because we're adding electrons that will increase the electron-electron repulsions. This idea of forming cations, removing electrons, that's linked to the idea of ionization energy. So if we're adding or removing electrons, it's easy to account for adding electrons. Electrons will always be added to the next energy level, the next spot that's available. So for fluorine, 1s2, 2s2, 2p5, I have room to add it to the 2p orbital, so the fluoride anion becomes 2p6. For cations, we have to be a little bit more careful. Cations are always removed from the higher energy level, and that energy is based on the principal quantum number. So this means we have to be careful with our transition metals. Take a second. What would be the electron configuration if I'm looking at iron 3+, neutral gallium, or gallium plus? You can use the condensed form for that. What would be the electron configurations? The reason I say we have to be careful with our transition metals is notice that we have both 4s and 3d electrons. So we would initially be removing them from the larger principal quantum number, which would be n equals 4, before we remove it from 3d. So in each of these cases, let's start with the correct initial electron configuration for the neutral atom, and then account for removing from the larger n value after that. So when we're removing electrons, we're talking about the ionization energy, the energy it takes to remove one or more electrons. First of all, here's our symbolism for that. A couple things that I'm noting. I'm interested in describing removing an electron from an atom in its gaseous state. Doesn't matter if it's something that I would associate as being a solid. I'm going to define the ionization energy as removing an electron from an atom in its gaseous state. The first ionization energy, I sub 1, is removing one electron. I could go on and remove a second, a third, so I can have successive ionization energies. So we want to know that symbolism. It's always going to take energy to remove an electron. It's always endothermic. The best way that I can predict whether it takes a large amount of energy or a smaller amount is based on the size of the atom or ion that I'm removing the electron from. The smaller size corresponds to a higher ionization energy. If we look at the data, here would be for hydrogen. Hydrogen is a small atom. Helium is even smaller, and it takes even more energy to remove an electron from helium. Smaller size, higher ionization energy. Why does that make sense? Well, we're looking at the attraction between the nucleus and the electron. The closer those are together, the lower the potential energy, the greater the attraction, the higher the ionization energy. After helium, I see it becomes really easy to remove from lithium now, because lithium now is in a larger principal quantum number atomic orbital. It's easier to remove it further away from the nucleus. And we see a general pattern then as we move across that row. We see a contraction in the size, and it becomes more and more difficult to remove the electron. So this relationship between size and ionization energy, really good part of the explanation. We see a few exceptions along the way. So as I move left to right there, I see a little exception here if I'm comparing nitrogen and oxygen. If we were to look at the atomic orbital diagrams for those, that would be my sketch. What's going on in that case? Why is it a little easier to remove an electron from oxygen than I would have anticipated? I would explain it this way. Even though oxygen has more protons than nitrogen, it appears that the electron-electron repulsions for this element, for oxygen, makes it somewhat easier to remove an electron than anticipated. It all comes back to the attractions and repulsions that are present. And it appears that placing two electrons in the same orbital for oxygen made it a little easier to remove one than I would have anticipated. I mentioned that we can remove one electron, two electrons, three. We can remove all of the electrons. This refers to the successive ionization energy. Here's the data to remove, for example, from sodium, one electron, and then remove the second one. Magnesium, one electron, two electrons, three electrons. After the staircase here, it's showing that it takes a great deal more energy to remove inner shell electrons. In each case, I see that it takes more and more energy to remove the second, then the third, then the fourth. But I see a large disproportionate increase when I begin to remove inner shell electrons. We want to be familiar with both of those ideas. Here's some data showing the successive ionization energy for a second row element. Something from lithium through neon. I see that it's possible to remove one. Takes more to remove the second, more to remove the third, more to remove the fourth, and then a lot more to remove the fifth. What element do I think that is? I think it's a best match for carbon. If I look at carbon, I could remove one electron, two electrons, three electrons, four electrons to get to having only two left. I'm now in an inner shell, closer to the nucleus. It's going to take a lot of energy now to remove that next electron. What I've been trying to do here is offer an explanation for why we see this dramatic increase, a large disproportionate increase, when I was seeking to remove one of those inner shell electrons. What questions do you have about this? Are you able to follow my explanation? Let's see if we can now apply those ideas. Consider these three elements. So I showed sodium, calcium, and sulfur. Which of these has the largest first ionization energy? Make a prediction, offer an explanation. What do you think? If we were thinking about this back in terms of size, It's going to be sulfur. Recall that we see a contraction as we move across the row because we have the effective nuclear charge increasing, but we're not changing the principal quantum number. So I'd see a contraction in size as I move from sodium across to sulfur, and then it gets much larger, and then I would see a contraction once again. But the smallest out of these is going to be sulfur, and that's the one with the largest first ionization energy. How about the largest second ionization energy? What are your thoughts on that? I think it's going to be sodium. In fact, I'm sure it's sodium. Can you explain why sodium has the larger second ionization energy when we're comparing sodium, calcium, and sulfur? Now, within your explanation here, you cannot include words or phrases like happy, satisfied, it wants to be an octet, it feels better being a noble gas. The electron only responds to forces, not to emotions like that. Not to emotions like that at all. So try to offer an explanation. Why would sodium have the larger second ionization energy? And we'll pick up from there.